Okay. Okay. Today we have to cover two, you could say two different lectures. First, we have to finish our conversation about filters, and then we have to cover mechanics refresher. Mechanics refresher is going to be quite simple, so I think we will be able to be on time. All right. So I'll just start writing. Last time we covered, by the way, let me know if my sound is okay. Uh, if there's some problems with my sound, please tell me. Please tell me. Okay. No problems. Great. Great. So last time we managed to cover how RL circuits work, right? We found how they work by suppressing, attenuating high frequencies and how they pass low frequencies. And we did it by analyzing them as differential equations, proposing a harmonic solution. And then we did the same thing using Laplace. So we saw how it can be done both ways. Now let's do the same, but with RC circuit. But we'll do it faster, since a lot of it is very similar. Okay. We begin by simply looking at what RC circuit is. So as before, here is a resistor. So this is a circuit. Here's a resistor. And the voltage across the resistor can be measured if you put your, multimeter right before and right after resistor. You would get a voltage across the resistor. Here is a capacitor. And again, voltage across the capacitor can be measured by putting your multimeter measurement connectors, left and right of the capacitor. So here's the input voltage. So this is it. This is the simplest RC circuit. Okay, simplest RC circuit. Okay, okay. If we don't have input voltage, it becomes even simpler. It becomes like this. If we don't have input voltage, what we are implying is that here, instead of a voltage, there is just a connection, just a wire going straight through. So this would mean that the circuit becomes short-circuited, right? Short circuit, so no input voltage. Okay. Now, remember a relation between charge and current. Yeah, there is a question. Okay. There is a relation between charge and current. A charge is the integral of a current. Of course, we could also say, plus initial charge. That would be more correct. Or plus initial charge. But if there is no initial charge, then this relation would hold. Which implies that derivative of a charge is equal to current. And that is always true. Initial charge does not change that. Okay. Now, that was just a definition of charge. To make progress, we need also a equation of a capacitor. Equation of a capacitor is this. It basically says that the voltage across a capacitor is equal to charge divided by capacitance, right? And this is, as I said before, this is analog to Ohm's law for resistor, or to equation of an inducer for inducer, right? So for inducer to be derivative of current times inductance. Here it is integral over current divided by capacitance, right? Because charge has is equal to integral over current plus initial value. Okay, so this blue equation is a equation of capacitor. With that, we can use voltage Kirchhoff law to construct differential equation. So here's the differential equation. Here's the, remember, Kirchhoff voltage law says that the sum of all voltages across a closed circuit should be equal to 0, where we conventionally imply that consumers of voltage have a one sign and producers of voltage have a different sign. So voltage input would be positive and let's say resistors, capacitors, and inductors would be negative sign, or we can just put them on the different side of the equation. That's what I did here. Okay, so this blue here is a voltage consumed, you could say, by the capacitor. Okay. This is Ohm's law, so the voltage consumed by the resistor. And here is the input voltage. So the sum of those have to be equal to that. All right. All right. But the variables are not homogeneous. We have charge and we have current. It's not very convenient. So what we can do is we can keep the charge in the characteristic equation of a capacitor, in the capacitor equation. Sorry. But we can replace current with derivative of a charge. Since we said that it's true, current is derivative of a charge. So let's do that here. Instead of current, we have a derivative of a charge. And we have this new equation now in just Q as a variable. And voltage remains the same. Okay. Now, what is interesting here is that this equation that we got at the bottom of the slide, equation 30, is a differential equation of the first order with two coefficients. Coefficient in front of the derivative. Coefficient in front of the derivative is R. This is coefficient in front of the derivative, okay? First order derivative. Coefficient in front of zero order derivative is 1 over C, okay? So first order derivative, coefficient is R. Zero order derivative, coefficient is 1 over C, okay? The right-hand side has no coefficient. It's just a V of T. Now let us look at the equation for RL circuit. Differential equation, the one that we looked at originally. So here's the differential equation for the RL circuit. And look what we have. Coefficient in front of the first derivative is L. So for the other one, it was R. For this one is L in front of the first derivative. In front of zero derivative, it is R. It was 1 over C for capacitor, for the RC circuit. By the way, I apologize for the noise. I cannot do anything about it. If you want me to speak up, let me know. All right. This equation is exactly the same in form as the other equation, except coefficients are different. So if we simply replace in our derivations L by R and R by 1 over C, we get the new equation. And since our mathematics, the entire mathematics that we did here, dependent only on like all of these, the short circuit analysis, all of these for analytical solutions, steady state solutions, all of that, even our analysis over input, harmonic input, all of this dependent only on the form of the equation. We can simply replace coefficients and we get correct results. For example, here you can expect instead of R, we would get 1 over C. Instead of L, we would get R, right? That's I'm doing it in my head, so I apologize if I make a mistake. So somehow it feels like we could simply reuse our reasoning because equations have the same form. That is very common. I mean, first order and second order linear equations there is only so much that they can be different in, because they're linear, they're first order or second order. So coefficients, there's like 2 or 3 coefficients. Uh, if you analyze it once, you can reuse this information very, very often. All right, let us go back to our circuits. So this is one thing we could do. We can just reuse previously obtained information. Okay, next. What we could also do is use Laplace. And I want to show you that this just using Laplace here is quite simple. We don't have to, how should I put it? It's very tempting to reuse previous information, but that sounds as if we did something very hard, and now we try to save and reuse this effort because we could not possibly bring ourselves to do it again. But that's not true. That's not how it works. So remember again, we have this equation that relates derivative of the charge to current. They're the same thing, right? In Laplace domain, derivative is s. So it means s times q in Laplace domain is equal to I in Laplace domain. Okay. So the same equation in Laplace domain looks like this. Okay. This also means that q is equal to 1 over c I. This, if like this should be if hopefully it should be familiar or become familiar later. 1 over c is a typical expression of integrator. In Laplace domain, when you see 1 over c, you see integrator. Just as c is the derivative, 1 over c is integrator. So this should make sense. Charge is integral over the current. Okay, now this allows us to change this equation into something different, right? First of all, this q can be transported into Laplace domain as 1 over ci, and that's what we have here. 1 over ci and 1 over si, so 1 over si, and we have c capacitance in both equations, right? Capacitance in both equations. The Ohm's law remains the same in both cases. And the right-hand side V remains the same in both cases. So we have, we have a differential equation, which is quite the same, but we have this 1 over c, 1 over s times c here. All right, sounds good. Sounds good. And notice this equation is now homogeneous in terms of current. So we don't have to go to charge. We can stick to current, and we have homogeneous equation. So this gives us a transfer function from current to voltage. So, sorry, from voltage to current. So what function should we multiply voltage by to get current? Well, how do we compute it? Well, we get current out of the brackets here, right? Notice it is homogeneous in current. So we have current here, current here. If we take it out of the brackets, we get 1 over cs plus r in the brackets. We want to make it into a single fraction. So we replace r with c r divided by s r divided by s, right? Something like that. And the SCR divided by SC. Okay. And then we write, invert. I think it is quite clear how we can express I from this equation, right? If you have questions, ask. I'm afraid to spend too much time on simple mathematics like this to, in case it is way too boring. Okay, but I can be expressed over here, right? So this is the expression. Now, this is a transfer function. So this guy here is a transfer function from voltage to current. Okay, sounds good. We got transfer function. Now, yeah, here's stated again. Now we can define transfer function from input voltage to voltage across a resistor, which is same as current but times R. Okay, that's current times R. Voltage across the resistor is current times R. Newton law. Oh, sorry, Ohm's law. So we get additional R here to our transfer function. That's it. We multiply it by R because that's how our transfer functions work, right? You want transfer from currents to voltage across resistor, you multiply by R. Well, you want transfer from input voltage to resistor, or you have first the one to current, right? This one is transfer function to current. Then you multiply it by R, and you get transfer function to the voltage across the resistor. Okay. All of this is you can say is related to the fact that we are dealing with linear systems, linear dynamical systems. So we have those nice properties of being able to multiply by a value and so on and so forth. Okay. Okay. By the way, all of this you can verify. Simply, you can construct this function from scratch, and you can see it's the same thing. Okay, transfer function from input voltage to voltage across the capacitor. We can construct two. How do we do it? Well, we notice that voltage across the capacitor is equal to 1 over CS times current. Well, we know what current transfer function for current is. It is this guy, right? This is transfer function for current. Well, we have to divide it by CS. So if we divide it by CS, what is going to happen is this is going to get cancelled, right? And then we're going to have 1 here. So that's what we have, 1. So the transfer function to voltage across capacitor is also easy to find, right? Okay. So we got transfer functions that we wanted for each for voltage across each element plus 2 current. Now with that we can do analysis. So frequency analysis again, remember, is done by substituting omega j instead of s into transfer function. So here is the transfer function for voltage across the capacitor. Okay. We substituted instead of s, omega j. Next step, we multiply it by conjugate, by what do you call it? We call it conjugate, right? The same expression, but opposite sign here, which would give us 1, since it is opposite sign, we have a minus sign here, but this will be squared, so it will be plus sign in the end. So this is what we have, right? 1 plus c squared, r squared, omega squared. And this is what we multiplied by. So we multiply, numerator and the denominator, right? So we multiply both sides of the fraction. And that's what we get. That's what we get. Now, after we've done that, we can find absolute value of this guy. Absolute value of this guy. Absolute value of this guy is can be found by as before. This is not we can get it out of the bracket because it's going to be squared and then taking the square root of it. It's positive, so we just need to find square of this plus square of that, square root. So this is what we have. And notice it is the same as the expression in the denominator, but the power is different. So it is square root in the numerator. Okay, I give up. It's the square root upstairs and the power one downstairs, right? Denominator. And here we have final expression. So 1 over square root of 1 plus c squared r squared and x squared. Sorry if it was a little bit long. We already did it a few times, but you can just see the process. It's quite simple. Now the frequency response for like a resistor, voltage across a resistor, is quite similar. I will just sketch you how it's done. So here is original one when we replace C with omega J. Then we multiply it as before by conjugate of this thing in denominator. We get this. Why? Because we have I here. So when we multiply, like stuff will change. I'm slightly worried that there is a minus sign lost as in the previous slide. But minus sign is not going to affect absolute value, of course. But yeah, and we get this out of the brackets, right? Notice it is in the brackets here twice. So we get it out of the brackets. And then what we can do is yeah, we get out of the bracket. Then when we construct absolute value, we have this and this out of the brackets because it's both positive values. They're going to be squared and square rooted. And the only thing that we have to do is find square of this plus square of this, right? Which, as before, will produce the same stuff as in the denominator, but square rooted. So square root will cancel, and this is the final result. Okay. So basic manipulations, same manipulations each time. Okay. So this is how we can compute this. Now let us analyze this last one, the voltage across the resistor. So when frequency goes to infinity, like this guy goes to infinity and this guy goes to infinity squared. Notice that here downstairs, the entire expression will be dominated by c squared, r squared, omega squared. This one will play absolutely no role. But square root of c squared, r squared, omega squared is c r omega. So this expression downstairs will tend to the same thing as the expression upstairs, right? And the gain overall will go to 1. So that's what is going to happen as the frequency goes to infinity. So the whole circuit will stop acting like anything. It will just pass frequencies right through when the frequencies go to infinity. On the other hand, when frequencies tend to 0, this downstairs will have this 1, which will dominate because c squared r squared times 0 is 0, right? But this 1 will dominate. And upstairs will have 0, okay? So 0 divided by 1 is 0. So as frequencies go to 0, the gain also goes to 0. What does it mean? Well, it means high frequencies will be passed unchanged, while low frequencies, such as constant signals, will be cancelled. This makes perfect sense. If you think about a capacitor tends to, it's just a broken line, essentially, right? Two plates and a broken line. So charge accumulates, of course, based on how much current you have. But eventually, it stops, right? The capacitor is fully charged, and after that, the circuit acts as if it is broken. And that's exactly what's going to happen. After transient process is over, on low frequencies, when you have constant signal, for example, the whole circuit will just stop passing through the um, signals, right? While for high frequencies, capacitor actually acts like it has no resistance whatsoever, right? So it will be it would have a gain of 1. So whatever comes in will be measured exactly over across the resistor. So capacitor will not take anything from the input voltage, and the entire input signal can be measured across the resistor. Okay. And you can say, based on Kirchhoff's law, alternatively, measurement across the capacitor will be exact opposite. So while this is high pass filter, it passes high frequency signals and cancels low frequency ones. If you measure across the capacitor, it will be the opposite. It will be low pass filter. You'll be able to pass through low frequencies. They'll be measured exactly across the capacitor, while higher frequencies will be cancelled. All right. So this is, you can see it is twin brother of RL circuit. They're very similar. They're very similar. Okay. Okay. Good. Now let me go to the next stage. Let me go to the next stage. If you have questions, ask me, please. Let us try to do RLC circuits. RLC circuits. Now, we need for that equations of capacitor, right? And equations of the inducer. Right? Equations of the inducer. Okay. The equation of the inducer give us this part of the Kirchhoff law, right? What is RLC circuit is basically just the 3 elements: resistor, capacitor, and inducer, right? Strung together. And we have input voltage. So Kirchhoff voltage law tells us that 3 loads will have sum of the voltages equal to the input voltage. So here is the characteristic equation of equation of the inducer. Here is the equation of the capacitor, familiar with this lecture. Here is Ohm's law. And we have our favorite of input voltage. Input voltage. Okay. Now, Laplace transform of this equation can be found by using replacing derivative with s. So this is input like voltage across the inducer can be computed this way because the derivative becomes just s, right? For the voltage across the capacitor, we have this expression that we found before. You can think of it as voltage is equal to the integral of a current times 1 over c. 1 over s is integral, right? And we rewrite it and we get the equation. Here is a inducer. Here is a capacitor. Here is Ohm's law, and we have input voltage. Okay. So after we express current, this is homogeneous in current. Okay, so this expression is homogeneous in current, and after we express current out of the brackets, we can get the expression for the current, which would be what I wrote here. Right. So this is the expression for the current. I think not surprising, right? how could you express it? You could multiply both sides by SC, and then yeah, then you would get this expression. Okay. So this is it. This is just we just expressed current out of the brackets. Okay. We could do it another way, but ultimately it is almost the same. We could say, all right, let us write this, derivative. There's Ohm's law, and here we write explicitly integral equation, right? Then we replace same as before. We replace integral by 1 over c. Notice this equation is homogeneous in the current. So this equation is at least homogeneous, but it is differential integral equation. We saw it in the first lecture, and we had questions about it. So yeah, here is how we deal with it, right? You can replace integral by 1 over c, derivative by c, or 1 over s, sorry, derivative as s, and multiply both sides by s squared, divide by l, and we get this, right? Here, this divided by L, multiplied by S, this is inductor. This is clearly a Ohm's law, divided by L, multiplied by S, right? And this is capacitor, divided by L, multiplied by S, S cancelled. And notice that we have here additional S squared because we multiply by S squared. Yeah. Sorry, you multiply by squared. Let me just double check. Let me just double check. No, I think the type. Here, what we should have is just S, just S. Okay, just S. No, not S squared, just S. Okay, that would be correct because we multiply by S, not by S squared. Okay. Now we can compute voltage across the capacitor by remembering this is voltage across the capacitor we can compute by remembering that we should here I skipped, I guess, the part where we get the final transfer function, which is unfortunate. Let us look at the final transfer function. Here is how it looks for the current, right? One. I also want to double check those things. So, is a little bit worrisome. It should be correct. I think this should be correct. Hopefully it should be correct. Yeah. So what we would do next to get transfer function here is we multiply by c both parts of this fraction, right? Multiply by c both parts of this fraction, and sorry, by LC, right? Both sides of this fraction. Yeah. Yeah. And then we get this. Yeah. Then LC should be in the upstairs. and this like LC like this, right? Plus RC plus 1 should be downstairs. Okay. Okay. I will double check all this after the lecture, just so we don't have any more typos. Right. My apologies. Right. So to find a voltage across the capacitor, we multiply this transfer function by 1 over CS, right? To find the voltage across the inducer, we multiply it by SL, right? So quite simple. And that is it. That's it. We could analyze this whole thing in terms of bandwidth, right? We could say, is it a low pass filter or is it a high pass filter? What will happen is we will substitute instead of S, J omega. We will substitute J omega, and then we would get basically a quite a bigger system that we had before, and we would have to somehow be able to tell what we would see is of course that very high frequencies are going to be cut off, very low frequencies are going to be cut off. That is the effect of capacitor and inducer in series, and there will be a band in between that is not cut off. That I didn't want to do explicitly here, but yeah, this is how it's going to work if we did it. We could always just plot Bode plot using Bode plotters. So essentially, if you have your transfer function, such as this one, you could just get it into the Bode plotter and it will plot you your frequency response. And that will be sufficient for you to analyze your particular circuit. All right. That that is good enough for filters. So do you have questions? I again apologize for background sounds. That's I cannot do anything about it, unfortunately. Not in my usual location. Do you have any questions? All right. Then I'll pause the recording, then we'll go to the next lecture.